Well, to the 1, 2, 3, 4, 5, 6, 7 of y'all, hi, hello. Welcome to section number 9. This section has a lot in it. It's going to be a little hodgepodge mode, but we are going to be broad strokes doing 1, radicals, 2, EAS reactions, 3, talking about directing effects, and then 4, how to study reactions, part 3, the threequel. I don't know. Last thing I would like to end off on, if we have time, is doing a hard synthesis with y'all, because I think it's helpful to do hard synthesis with you so that you see how to approach it and break it down. So it's one of the extra challenge problems. It's one of my favorite syntheses in the whole class. So we will see it and try to get through it. It's been lovely meeting with you all. I think I've met with everyone in the class except for like 3 people. So it has been a week. We are tired, but has been well worth it. The QR code today, Miss Benzine, you know her lore, you know her mysteries, and now you know a little bit of how she reacts. She does a whole other family of reactions that we don't teach y'all called NAS reactions, nucleophilic aromatic substitution, and those are fierce, but you will not see them here. So, work. Any questions before we jump in? So, let's talk about radicals. Now, radical stability follows the same exact trend as carbocations. Remember, carbocations were a deficiency of electrons, but when we have a radical present, we have a half-filled orbital, so we also have a deficiency of electrons. So it makes sense that the things that would stabilize a carbocation stabilize a radical as well. And so we have that secondary and tertiary radicals are more stable than primary and methyl, and it's because of hyperconjugation. But then we also have radicals next to pi bonds as being quite stable based on resonance. And drawing the resonance structures with radical arrows is a little bit weird. But remember, when we're showing one electron moving, we do those, quote, single fishhook arrows. So if I were to draw the resonance structure for this, it would be one electron comes in from here, one comes in from this double bond, and then the other electron in that double bond goes out on the edge. And then that's going to give me this resonance structure for our radical. So she is spreading out the deficiency of electrons, very stable. Well, with that, we have our kind of general line reaction, the kind of bread and butter one that we teach you. That's going to be the one that's fair game for like synthesis and line reactions. And this is for the anti-Markovnikov addition of a bromine to an alkene. So in terms of our like what, where, and how, the what is it's adding an H and a Br. The where is it's adding anti-Markovnikov, so it puts the more electronegative element on the less substituted side. It's only the second anti-Markovnikov reaction we teach you other than hydroboration oxidation. So be on the lookout for that. And then the how, for syn versus anti, it's going to be mixed because you're doing radical things. So you're not always going to get syn or always anti. Now, I do have like a little FYI box on more of the radical reagents. So we put ROOR, like a peroxide here, which I heard someone call ROR. And I was like, ooh, I love that. ROR, radicals. But we can use a lot of different initiators for radicals. We essentially just need a single bond between 2 electronegative elements because those are ones that can radicalize really easily. And so you will see examples of other ones on the problem set other than just the generic one. We also either put a delta symbol or HV to represent either heat or UV light that kind of initiates off the process. But that's more of an FYI. Our general mechanism, and I should say there will be a radical mechanism either on exam 2 or the final. It's kind of like the DCC synthesis. There definitely will be one, but it will be either on exam 2 or the final. And it's unclear which, because I have not written it yet. Fun things to do over the weekend. Ooh. But in the past, like in both the practice exams, I believe there is a radical mechanism. So I think that we might just go ahead and do it on this exam. When you're doing a radical mechanism, the initiation should be easy points. It is almost verbatim the exact same time. Like this should be something that you can just like bang out and write. So you homolyze the OO bond, which means just split it in half equally. And then you get 2 RO dots. Then RO dot interacts with HBr. It is going to grab or abstract proton and make this into just an alcohol. And then we get RO dot, which is our main initiator for the reaction. So phase 1, again, of radical reactions, always the same. Phase 2 is propagation. So it's going from one radical thing to other radical things. And then the final phase is termination. So we have the initiation where we generate our dotty boys, propagation where dotty boys make more dotty boys, and then termination where dotty boys come together and are no longer dotty boys. So propagation here, this is the bulk of the actual reaction, and this is where you can see some variation. So what we have is when we have our Br dot, she is going to interact with our alkene. The alkene pi bond is going to split, and one electron is going to go over, combine with Br dot, and create a new sigma bond. And then the other electron becomes a radical on a carbon. Now, hypothetically, we could have split this up to put our radical on the end and our Br in the middle, rather than what actually happens over here. But why do we not do this? Who is more stable? A secondary radical or a primary radical? Secondary radical, exactly. So it's just like carbocation stability. But here, comparing this with HBr without radicals, the first thing that we add in the HBr without radicals is a hydrogen. And so we form the more stable carbocation exactly where we form the more stable radical here. But we're just adding a Br first instead of an H first. So that's kind of why it changes and why we get the anti-Markovnikov. All of it is following this principle of forming the most stable radical or carbocation. Then, once we have a radical over here, then we just need to add the second thing, which is a hydrogen. So it's going to interact with another equivalent of HBr. It will take the hydrogen, and then we get another Br dot, propagating on, doing more of the reaction. So this is, again, the bulk of the actual radical mechanism that you will be doing. And this is the most straightforward one you will see. But as you will see in these practice, they get harder and do weird things. Yay! Last thing is termination. This is kind of boring where the dotty boys become no more. And we often will say don't write in termination steps because we don't care. But basically, any things that have radicals in the entire reaction beaker could combine and then just suddenly stop. So a Br dot could encounter another Br dot, in which case it forms Br2, stops. We could have this intermediate from, once we've added the Br on the molecule, interact with another Br dot, in which case we get this little side product where we have 2 bromines. But just think about I keep wanting to say economies of scale, but that's not it. Think about relative abundance. If you're doing this in HBr as your main solvent or the main molecule that's present, it's going to be much more likely for this to interact with an HBr than it is another Br dot, which is our kind of initiator that's almost catalytic in amount. But it could happen. Hey, anything could happen. I don't know. These are crazy times. So this one right here is a standard reaction. Don't get me wrong. But radicals do crazy things, crazy chemistry. And we want to show you a little peek of that. In the same way that we showed you the standard carbocation rearrangements of the methyl and hydride shift, and then we said carbocations do funky things, we are also going to show you that radicals do funky things. And I think that there's a very specific approach for radical mechanisms that can help you break down those weird steps and figure out what's going on. So that's what I want to do with y'all for the next little section. Notably, radicals can open rings and form rings, which is kind of unique. But let's talk about advice for doing radical mechanisms. The most helpful thing you can do by far is number your carbons and map the starting materials onto the products. Because again, if it's going to do weird arrangements of busting open rings or making rings, we want to know where the bonds are that are actually formed. Once we map the starting materials and products onto each other, the other main strategy is to make a make and break list of all of the bonds that need to be made and broken. With that, one thing to watch out for is hidden hydrogens. So, like, for example, just this super basic one where we're going from this to this. If you're doing analysis of just starting materials and products, you might just be like, oh, we broke the pi CC, and then we made a sigma CBr, but in fact, there was a hydrogen that was added here that we just didn't show because we can imply carbon-hydrogen bonds. So we also had to make a carbon-hydrogen sigma bond. So watch out for that when you're doing your lists of the hidden hydrogens. And then also observing norms. So like most radical steps involve 3 arrows at a time, which is kind of weird. And I know that like doing radical arrows, y'all barely got non-radical arrows like down. So it feels like a kind of left field move. But you will start to see really like common things that the arrows will do of these kind of 3 at a time. But without further ado, let's look at this practice. So this is a skill builder, and then we're also going to do a challenge problem. Okay, so we need to map the starting materials onto the products, and this looks hellish. Because, like, I'm pretty sure this double bond is not just straight up this double bond. This double bond's at the end of something that's in the middle. So what I'm going to do is I'm just going to start numbering in the products. So, like, 1, 2, 3, 4, 5, 6, 7. Another thing that I'm going to think about is what is the first step when our alkene reacts with the radicals? Anyone? Yeah, we're going to add the bromine, right? So let's think about this. If this is our alkene and this is our bromine added at carbon 1, does it seem likely that this could be carbon 1? No, yeah, it is.
Oh, it is?
Yeah, no, totally. Because the first thing it's going to do is go and react with Br dot.
Oh, right, yeah.
And so I think it makes this a really likely choice to be carbon 1. So if we try to do this and map this out as carbon 1, this is going to be kind of the site that does the big starting off. Then we can continue to number around 2, 3. And if I'm trying to get a straight chain, it would probably make more sense to count around this way rather than to count down and back or something. So 3, 4, 5, 6, 7. So in terms of finding our anchor point, thinking about the mechanism of like adding the Br to the alkene is going to be a great place to start. And now we can make our make and break list. So you all are going to be telling me what to write. I want you to tell me a sigma or pi bond that needs to be made or broken in the course of this reaction just by looking at like mapping these starting materials onto the products.
Sigma bond, carbon 1 and Br.
Carbon 1 Br, that's a make. Great. Sigma, I'm going to do 1 Br just because like carbons, I think it's more helpful to use the numbers on these lists. Cool. What else? Pi CC we have to break. Oh, and also. So we need to break the 1,2 pi bond, and we need to make a 2,3 pi bond. Great. What else?
Sigma CH bond on 2.
Sigma CH bond on 2. Well, carbon 2 has 1 hydrogen here and still has 1 hydrogen here, so not exactly. On 1? Well, 1, we have the bond to Br, right? Because this already had 2 hydrogens. She still has 2 hydrogens.
Sigma, we need to break the bond between 3 and 6.
We do indeed. And that's going to bust the whole thing open, right? So we need to break the sigma 3,6 bond. And there's one more make.
Oh, sigma CH on 3.
Yeah, in its place. So this carbon 3 has 1 hydrogen on it, which I drew kind of weird. And here, it has 1 hydrogen. 6, thank you. So 6 here had 1 hydrogen, and over here it has 2 hydrogens. That's what I mean about the hidden hydrogens to watch out for, because oftentimes we've added a hydrogen, but it's unclear where it is based on how we drew the structures. So we have the sigma, I'm going to do 6H. Does that seem like a complete list? Yeah, it looks good to me. Let's try it out. So, first thing that you are going to do each time is straight up regurgitate the arrows, which I need to figure out a better word, because that word's a little gross, because it does feel like mother bird feeding the children. But I mean, kinda. So, starting off, we do this the same every time, and I'm going to write it as fast as I possibly can so I can then start thinking about the real reaction. ROOR, we homolytically cleave. We get 2 RO dots. RO dot interacts with HBr. These come together and form HOR plus RO dot. Or sorry, not RO, BR dot. And this alone, I think, will be like 2 or 3 points on the exam. So if you can get to where you do this, which is almost the same every time, just watch out if we don't have ROOR and we have one of these other initiators. It's the same exact arrows, no matter what. So now we have our starting molecule, and we have BR dot. Well, we said that the first move is normally interact with the alkene, add the bromine in its place. So let's do that. So 1 electron in the pi bond is going to combine with the RO dot, and the other electron's going to go on carbon 2 over here. Cool. So we have 1, 2, 3, 4, 5, 6, 7. So in our goals list, we can check off we have made our 1 bromine, and we have broken our pi 1, 2. Already accomplished 2 goals. Wow, so easy. So now, in pursuit of our other goals, which of these bonds do you think we should try to make or break next? Well, we have a radical on carbon 2. So, do you think that we should do a bond to make or break that involves carbon 2? Yeah, it's like our reactive site now. So, what involves carbon 2?
That's pi bond.
So let's try to make that, but in making this, we can do 1 electron in from here. Where should we take another electron from?
The 3-6 bond.
The sigma bond here that we're trying to break. So we're combining our make and break goals to figure out what the next step is. Cool. So this one folds in here. 1 electron from the 3-6 sigma bonds goes there, and the other electron goes on 6. In doing that, we made our pi bond. We broke our 3-6 sigma. And now we are so close to the end. What is our only thing that we have left to do? Yeah, add an H. So this is where we get another equivalent of our HBr. And the dotty boy does what the dotty boy does. And we are at our product. And who lives to dot another day? A BR dot. You don't have to draw that, but like, yeah. So we have our initiation up here in the light blue, and then our propagation. Or propagation. Cool. So this is like a pretty straightforward radical mechanism that involves a ring opening. Questions about her or the process? Are we ready for a harder one? So, ew.
Okay.
Zoinks.
Is that like a Scooby-Doo thing?
Yeah, it is. It is like the Scooby-Doo thing. Yeah. For some reason I thought Scooby said it, but no, it is the human saying zoinks. But here we are. So, first off, What is our tip off that this is a radical mechanism?
The epoxide, or no, sorry, the cyclopropane. Like HV make or break reactions, right?
HV. This is saying that we have UV light, and either that or heat is what's going to like homolyze bonds between electronegative elements. And then we don't have ROOR, but do we have any single bonds between electronegative elements?
There's an oxygen and nitrogen.
Good. So our first step is just going to be this bond homolyzing. So we can do that. And maybe I'll draw the next one. I don't care about all of that. So what I'm going to do, on your actual P-set, or on an actual exam, you should draw out things. But what I'm going to do is I'm going to do R, because I don't want to draw it, simply. Okay, so we need to do some mapping over here. I mean, the thing is, all of this looks pretty the same, right? So why don't I start numbering like 1, 2, 3, 4, 5, 6 here. And actually, I'm going to go back and do that in red. So I know that this gotta be carbon 1 over here, right? Because that's still part of the molecule that stayed the same. So let me continue counting 2, 3. Now, it's unclear, like these have to be 4 and 5 somehow, but we don't know what order it is, correct? Does it matter, do you think, if we do 4, 5 or 4, 5? It doesn't matter, actually, because this is symmetric. So it's kind of like when you were doing like branching for deciding rules, and we were like, which path do we go down? They're the same. So just number it however you want, and then you can use that to guide you. So 4, 5. And then our 6 was the nitrogen here. So let's do our analysis, our make and break list. Someone give me a bond to make and or break.
A pi bond between carbon 3 and oxygen.
Yeah, we need to make a pi between 3 and oxygen. And it looks like this oxygen in pink is going to be this one right here. Because otherwise, I don't know how else that happens. So that's one bond that we need to make. What are some others? Sigma CN, great, and that's going to be between carbon 5, good. So sigma 5N, cool. Yeah.
That's like sigma 4-3 or 5-3.
Yeah, and just based on how I numbered it, which one do we want to break? Yeah, 3 and 5, because 3 and 5 are not connected here. But you can imagine they were like this, and now we are kind of busting it open. So we need to break sigma 3, 5. Any like sneaky hydrogens or anything? On 3? No. No, I think this is it. Yeah. So, like, I mean, with this in mind, let's do it. We did our first step of homolyzing. We broke the ON bond. So now we have radicals on nitrogen and on oxygen. So we probably want to do a goal that involves one of these. Which do you want to try to do? The 3O pi bond or the 5N sigma? I would say let's try the 3O, because we know pretty reliably that that's going to form the carbonyl here. So we need to put one electron down into this to form a pi bond. And then we need to get another electron from somewhere, so let's look at our break list, breaking the 3-5 bond. So let's do this. one electron from the 3-5 bond goes in to make that double bond. The other electron goes on 5. So when we do that, we had our 1, 2, 3, 4, 5. And then 3, we now made a double bond on it to O. And then 5 has a radical. We've checked off 2 more of our goals. Now, does anyone's alarm bells go off when they see this radical?
Yeah. Because
Yeah,
it's primary.
it's primary. Unstable. So, primary radicals can exist in a way that primary carbcations won't, and it's because it's only half filled for the orbital, not completely empty. So it can happen, especially in an intermediate step in the propagation. So it typically is not going to happen in the initiation or like the first step of a radical reaction kicking it off, but in the course of this molecule undergoing rearrangements, it can happen. So I'm going to put OK in the middle of the reaction. So now we only have one goal left. And we're done. So again, this is one where it looks super hard. All in all, it was 3 steps. And so this make and break strategy really, to me, turns it into a very formulaic type of question, even though you are doing crazy ass shit with like, I mean, if I had asked you a week ago to go from a 5-membered ring and a 3-membered ring to a 6-membered ring and like make a carbonyl, you'd be like, ah. But like, when we break it down this way, it's kind of the only thing that could have happened. So, do you feel like the radical question on the exam is going to be something that will be doable? Even if I write a hard one? I don't know. I've never written a radical question, so we'll see how it goes. Yeah.
Why can we break the NO bond like that? Is NO particularly weak?
So it's typically just bonds between 2 electronegative elements. Whenever we have a sigma bond between 2 electronegative elements, it is just particularly unstable. And to be so honest, I don't have a good explanation for you. I think it has something to do with MO theory, something to do with quantum mechanics, but like, I just said, cool, I'll take that. So I know that that's not a satisfying explanation, but it is what I have for you at 9 a.m. on a Friday. Cool. Any other questions with radicals? Yeah.
Would it be better to have them between 2 with the same electronegative atoms, like easier since they'd be like symmetrical?
Beyond my pay grade, so also certainly beyond your pay grade. Yeah. Sorry, that came off as really like mean. Don't worry about it. That's what I meant to say. But great question. Maybe ask Logan. Yeah. Okay. I think that's radicals. Oh, I should have done this transition in getting into it. The radicals. It was. This was for stranger rearrangements. And so maybe I should have done stranger radicalization. I don't know. I don't know. But here we are. So now the vibe of EAS reactions are like bright and light and fun. And my like little story is I first learned these reactions when I did OChem 2 in spring 2016, my senior spring of high school. And it was right after Beyonce's Lemonade came out. And I remember going to a coffee shop at 8 a.m. when it opened, listening to Lemonade on repeat for good 12 hours and just doing EAS reactions and the other ones that we don't teach you, NAS reactions of benzene. And so that is forever my like place memory with these reactions. And so it feels very coffee shop Lemonade vibes. The purpose of these is to add chemical groups to a benzene ring. And the logic behind these rings is aromatic rings are really stable. Like they have aromaticity, they're just vibe on their own, so they're not good nucleophiles. So because they are not good nucleophiles, we need to make awesome electrophiles. And to make these awesome electrophiles, they need to be made in situ, like situationally made, kind of like in a beaker. It's not something that's just going to sit on a shelf. Most of the things that can sit on a shelf stable are not going to be electrophilic enough for a benzene ring. So we have to make these really, really good electrophiles. And the general mechanism, super easy. Benzene goes and grabs an electrophile, and then we remove the hydrogen that was also on that spot. So when this double bond grabs something, we briefly have a carbocation, and then we have a hydrogen here initially, so we have another hydrogen. And then in order to reform the aromatic ring, we do an elimination. So that is her. The tricky part with the mechanisms all come in forming this good electrophile. But first, let's meet our stellar electrophiles. Oh my gosh, this batch, they're so great. So, we need to make a better electrophile for halogens, which we do with these Lewis acids, electronic acceptors. And essentially what it does is it makes them, like once we associate our Br2 or Cl2, it makes this whole thing an excellent leaving group. So our nucleophiles can just come in and attack the Br or the Cl. Then the second family are these deactivating acids, so we can add an NO2 or an SO3H. And for these, use HNO3, which is cute, I guess, nitric acid. We need to get NO2+. Like the way I remember it is I remember NO2+. And I say, okay, how did we make this? Well, we needed a leaving group. We needed an alcohol that we turned into water. And then we did a lone pair push and kicked it off. Then for SO3H, you just start off with SO3, sulfur trioxide, which she is giving runway. She's giving symmetry. And then in order to make it a good acceptor, we just need to like protonate one of the carbonyls, sulfonyl things. And then our nucleophile just attacks and breaks the pipe. Yeah.
So when you're thinking about like synthesis reactions and Box problems, your first step would, I guess, for both HNO3 and sulfur trioxide would be like H0+.
Not exactly. We'll get to the reagents in a minute. Right now, we are just showing the mechanisms for forming these good electrophiles. But this is all thinking at the mechanism level. At the line reaction level, we'll talk about it in a minute. Yeah. But we do need a strong acid in order to protonate nitric acid. And to protonate sulfur trioxide, we need something that's a really great acid as well. So, well, actually, we can go and look at it now. So I made a little reaction web for you.
Oh, hell yeah.
Yeah. So, bromination or chlorination, we just need to add our Lewis acid with FeBr3, AlCl3. Yeah, the mnemonic of like doing iron with bromine that I remember is like, bruh, I need to lift iron at the gym. Bruh. And then this is like, I don't know. I don't have mnemonics. I'm trying to make one up on the spot, but like, I'll call Al. I don't have one. I don't have one. It's bad. It can also be FeCl3 and AlBr3, I believe, but these are the most common ones, so that's why we have it here. But it does feel like another thing to memorize because it kind of is. So with the ones that we were just talking about, the sulfonic acid and the nitro group, we have our sulfur trioxide and nitric acid here, and we need to do it with concentrated sulfuric acid here. And again, Logan said it's telling that we have to use these strong acids because in order to get the benzene ring to react as a nucleophile, we essentially need to boil it in acid. So she's normally just chilling. We really have to like rile this up in order for anything to happen. But when you think about this, because the activated electrophiles are these in situ ones, you not only need to know these reagents, but there's also going to be a separate mechanism for how we get from these reagents to the activated electrophile. And so thinking about that at a few levels of you're memorizing reagents, yes, you're memorizing how to get to the activated electrophile, but then once you have your activated electrophile, it's all the same reaction of this simple EAS one. Where is she? It's all her. So again, once you have the activated electrophile, then the rest of the mechanism is easy. So the only weird things to memorize here are the making of these electrophiles. And if we ask like a mechanism question on lecture 9, which seems to be likely in some form or fashion, there will be some mechanism that involves like benzene, then we will want you to be able to form these activated electrophiles that will be part of it. The last family that we didn't talk about are the Friedel-Crafts families, and these are the way to install carbons onto the ring. So we can either install carbons as just an alkyl group being added, in which case we use like an alkyl halide, alkyl chloride with AlCl3, or we want to install a carbonyl, like an aryl ketone is what we call it. So for this, we would use an acid chloride and AlCl3. One thing I want to flag, though, is an aryl ketone we can always reduce to just an alkyl group over here. And the way we do that is, what's step 1 do to a carbonyl?
Reduces it, so it's just OH.
Yeah, it makes it an alcohol. What does step 2 do? Concentrate H2SO4.
Makes it an alkene.
Yeah, we're doing elimination. And then what does H2 palladium on carbon do to an alkene?
Makes it an
Adding hydrogens. And so we can form alkyl groups either through Friedel-Crafts alkylation, or we can do acylation and then reduce it away. Does that make sense conceptually so far? Yeah.
Why would you use one over the other?
We're going to talk about that. That's literally the next topic. Izzy, the segues, they're all here. The thing that's frustrating is that this is 3 steps. In previous years, we've taught this as being 1 step, and I think it might still be in the answer keys for some of the things I need to update, where like we've just done that you could do H2 palladium on carbon directly from this carbonyl, which some textbooks say that you can use and some say that you can't. And I think this year Logan wanted to do the 3-step way. There are also other ways of reducing aryl ketones that are really cool reactions that we are just not teaching you because we are already giving you so many. Yes. Cool. And so the Friedel-Crafts alkylation versus acylation. For alkylation, what you do is you associate with AlCl3, and then your leaving group typically leaves, you form a carbocation that the nucleophile attacks. The other thing is, in past years, we have only taught this being with secondary and tertiary carbocations, but we can also do this with primary carbocations, and it doesn't go through a carbocation intermediate. Like carbocations, this is SN1-like, but there's also a way that we could do this, where if we have our Cl, AlCl3 minus plus, our benzene ring, our nucleophile, can just do an SN2 backside attack, and that also works. So keep in mind about that. I will make a note here, or do SN2 for primary. For the Friedel-Crafts acylation, it's a little bit weird, but the chlorine associates with the AlCl3, just like we've seen in the Friedel-Crafts alkylation and in these like halogenations. And then you push down and form a carbon-oxygen triple bond with positive charge on the oxygen, and this leaves. Now, I think Logan showed it in 2 steps. You could show just step 1, this leaves, and then step 2, resonance, but it's just easier to show in 1 step. Both are fine. So let's talk about Izzy's question here of why would we do one over the other? Okay, so if we are doing this first one, it looks like we are doing Friedel-Crafts alkylation. So the question that we should ask if we're doing alkylation is, did we go through an SN1 or an SN2 mechanism? Well, this is firstly going to associate with the AlCl3. You have a minus, a plus. And then what happens? SN1, does the leaving group just leave, or do we do an SN2 attack? Why? It's primary. So if our leaving group just left, we would have a primary carbocation. So no. Bloop. SN1. So we are going to be doing SN2 on this. So our benzene ring can come down and do an SN2 attack. Bloop. Kick off. And then we continue with the rest of our mechanism. So we had our group go and attack. I know I drew this bond going, but can you imagine that I rotate it and I just put it up here? Just for writing, it makes it a little easier. And then something in our solvent comes and does the rest of the EAS mechanism. So we can get our product that looks like this. So this is one where we have to just be careful about the SN1 or SN2. But then let's look at this one. We associate first. And then is she going to do SN1 or SN2? Well, it's going to form what type of carbocation? Secondary. And we said that this is not a good nucleophile, right? So our main option is just going to be SN1. It's only rarely going to do the SN2 when you have a really accessible backside attack. So our benzene ring is going to come over. Nope. Our leaving group's going to leave, sorry. So then what we get is this carbocation. Now at this point, what's going to happen? We got a secondary carbocation adjacent to a tertiary carbon. So the hydride needs to shift over, and what we get is this carbocation now. Gross. So now we would go and attack, and we would do the rest of our EAS mechanism, and the product that we would get here looks like this. So we've connected it at this carbon that used to be this tertiary carbon. And the other issue that I should say with this is a 1, 2, 3, 4, 5 neopentyl group. So remember, this SN2 is going to be incredibly slow. So even though this is hypothetically possible, like we can get this, it's going to be low yield. So this whole thing is, what if we want to get, oh, did I delete a carbon? I 100% deleted a carbon up here. I'm so sorry. So like we had these 3, and then 2, 3, 1, we need another carbon. So 1, 2, blum, blum. Nope, I did the exact same thing. 3, 4, 5. With these, it's always easy to just miscount and add an extra carbon or lose a carbon. Yeah.
Why is it very slow?
So this looks primary, but we do have this big isopropyl group nearby. And so it's actually not as fast as a primary because there is still steric hindrance with this. Yeah. Thoughts, questions? So essentially I just showed you 2 things that are not great, right? Like we have sometimes this is very, very slow for the Friedel-Crafts alkylations. Sometimes this is going to rearrange and not get the thing that we want. So how could we get this thing that we do want in a high yield? Well, our strategy could be we do an acylation, which is really fast, and then reduce it. So that is where we can kind of think a little bit more conceptually about this of, do we want to go through the acylation route or the alkylation route in terms of our yield? And acylation is typically just much more reliable. So let's ask this question of to alkylate or acylate here with some of these. So first off, let's just think back to if we alkylate or acylate, what are our reagents going to be? What are our intermediates going to be here? So for this one, if we were doing Friedel-Crafts alkylation and we wanted to do a carbocation, we would have this carbocation. Is that ever going to happen? No. So the other option for alkylation is doing the SN2 version. So we know that we would be doing SN2 for this one. Does this seem like a pretty accessible SN2? Is there any branching? No, so this should be okay. And then our other version here would be doing acylation, where we form this, which would come from this acid chloride. That seems fine as well. So we have two options that work here. Both the Friedel-Crafts alkylation and acylation works. Let's look at the middle example. So for this middle example, we would have this carbocation for SN1. Is that a good carbocation? No. And then for SN2, we'd have this with our leaving group. Now, it is primary, but do we have branching? Yeah. So for SN2, again, this is going to be kind of slow. So this isn't going to be a good candidate for SN1 or SN2 alkylation. However, if we thought about it from the acylation side, we know that we could form that carbonyl there and then do our three-step process and reduce that all the way down to an alkane. And this would come from an alkyl chloride that looks like this. So, the first example here, both of these were good. The second one, only the acylation was good, and then the alkylation was not as good. And then for this third one, well, in terms of alkylation, we start off with the carbocation SN1 version. Is that an okay carbocation? It's okay. It's secondary. It's going to be a little bit slow, but it's okay. SN2, we're not going to really consider here because secondary, again, it's not going to be very accessible. But I will write it just for completeness. And then over here, for acylation, what would that look like? Is that okay? Is that a yeehaw? Yeah, and that's where I need to add my "This Ain't Texas" sound. Let me see. This ain't Texas. Woo! Oh, it's gonna keep on going. So yeah, this carbon would have 5 bonds, so this one is just not possible. So in this case, we would have to go through alkylation, and we could not go through acylation. So do you see how this question of to alkylate or acylate can be a bit conceptual and could be turned into something like an exam question of like, why is it not going to be preferred to do acylation versus alkylation or something like that, hypothetically?
But is that you can kind of always do acylation unless it's actually not possible.
Yes, and that's the thing. Acylation is very reliable. And again, if you had a one-step way of reducing aryl ketones instead of 3 steps, so powerful, so powerful. But because we're doing the 3-step version this year, less powerful, less powerful. Cool. So we have our takeaways here of the acylation, as long as it's not this like tertiary, it's good. And the alkylation, secondary or tertiary carbocations that can't rearrange would be the safest bet. Yeah.
So in the last one, we did, like, you kind of crossed out SN2,
Yeah.
but SN1 was okay. Now, if we go back to what were the criteria, it was like, it would be fair for both, right? Because it's a second degree carbocation, but
It would be fair for both, but then the thing that would bump it is your benzene ring is not a good nucleophile. So for SN2, it would be...
SN2 would be bumped down.
Yes, exactly.
Okay.
Yeah, because a benzene is both bulky and a bad nucleophile. So again, we really have to tee it up for success with EAS reactions with these amazing electrophiles.
Right.
Cool?
Thank you.
Yeah, totally. Well, again, I feel like this, mostly because we've added the SN2 version of Friedel-Crafts this year, This felt a little clunky to me, and so like me going over it with y'all. So apologies about that. Again, 8:30 a.m. Y'all are the guinea pigs, and hopefully it'll be better in 10:30 and then 12:30. Just on the money. But let's see where we go next. So, directing effects. This is the big kind of theory question, and this is the thing that we are going to get at on one of the theory pages of the exam. So you will have one page of the exam, you'll see it on the practical exams, where there are kind of bubbles of like, where does this thing direct, or which of these is more or less activated. So the theory side of this, we love. So relative position nomenclature on benzene rings. So if we have some sort of R group on a benzene, then we call the positions next to it ortho, then we call the position opposite of it para, and we call the positions in the middle of those two meta. This changes based on where our R group is. So if I consider this to be my R group, then the pair positions opposite it, orthos, are right next to it. So like, for example, what is the relationship between X and Y? Ortho. What about X and Z? Meta. What about W and Z? Meta. And then finally, WY? Para. So again, very relative in terms of nomenclature. But let's talk about this. So benzoic acid, you know her now, right? Benzene with a carboxylic acid, benzoic acid. Now, if you make a peroxy bond, an OO bond, it's peroxybenzoic acid. And then if you stick a chlorine meta to it, it's metachloroperoxybenzoic acid, MCPBA. That's who she is. I just think she's neat. Yeah, so again, we snuck in like benzene chemistry before y'all even knew it, or at least the naming of it. So, now you know. Substituted benzenes. We have a few questions to ask if we are not just starting off with a blank benzene. One question is, if there is an R group already on the molecule, how does that R group affect benzene's reactivity? Does it make it more reactive towards EAS reactions or less reactive? And that's going to be a question of whether we have electron donating groups or electron withdrawing groups. If we donate electrons into the ring, we are making that ring have more electron density. It's going to be a better nucleophile. Whereas if we are withdrawing electrons from the ring, we are taking away electrons that would otherwise go and attack. So we're making a worse nucleophile. So that's question one. Second question is directing effects. So if we already have one R group on our benzene, how will that direct where the second thing will be added? Will it add ortho, para, or meta? And these are controlled by resonance. So key fact number one, electron donating groups are activating, and then they direct ortho para. So what we have is, if we have an NH2 group, this has a lone pair that we can donate into the ring via resonance, and if we draw out all the resonance structures, what we get is a negative charge that bounces around the ring, and it specifically goes to the ortho and para positions to our R group. So what we see is these carbons are slightly more electronegative based on their resonance structures, so they are going to be the more nucleophilic sites. So we add at the ortho and para positions for electron donating groups like this. If we just had an alkane, we say alkanes are also donating, but do they donate by resonance? No. What do they donate by? Hyperconjugation. So the same kind of donation that stabilizes carbocations. So now, we said that these electron donating groups are ortho-para directing. How can we choose between them? Well, oftentimes, if we have a small R group, like just a methyl, ortho is going to be favored just because you have 2-to-1 ratio. So like 60% to 40%, it's basically like 2/3, 1/3 split. However, if we have a really bulky R group, that's going to direct primarily para in order to minimize sterics. So electron donating groups direct orthopara and are activating. Key fact number two, electron withdrawing groups are deactivating and direct meta. So if we have something like a carbonyl on the outside of the ring, we can take electrons out of our ring via resonance. And then what's bouncing around instead of a negative charge is a positive charge now. So what we have is the ortho and para positions are relatively electron poor. They have a partial positive charge. And so the metacarbons are relatively more electron negative. It's kind of like these are the only two carbons that aren't bleeding. The other ones are bleeding, so they are not going to go and do an attack. So that's why we get electron withdrawing groups direct meta. Another way that we could have an electron withdrawing group that's not via resonance would be something like this. If we had a positive formal charge outside the ring, that is also going to direct meta and going to be withdrawing. So how does it withdraw if it's not via resonance? Induction, thank you. And the last kind of note here is that nitro groups and sulfonic acid groups are so deactivating that they are going to be shutting down Friedel-Crafts reactions. Did Logan say just nitro groups in class or nitro and sulfur groups? Just nitrogen?
Yeah.
Then I guess you shouldn't worry about it. But sulfonic acids are quite withdrawing. So actually I'm going to leave mine, and I don't think that really affects any problems. But like, just know if it's super electron withdrawing, like a nitro group, then we can't do Friedel-Crafts. Cool. So this is all summarized in a Gaussified chart for you. We have our strong activators. These are things with lone pairs that can directly donate via resonance into the ring. Our moderate activators that have lone pairs, but they have resonance on the other side as well. So it could donate into the ring, or it could donate into a carbonyl. And because that's split, it's not as good of a donor as the ones that don't have an option. Then we have our R groups, alkyl groups that are weak activators that donate into the ring. And we see all of our activators are going to be orthopara directors. In our deactivators, we have the halogens. The halogens are deactivating via induction. Then we have like carbonyl compounds with their carbonyls right next to the ring. These are moderate deactivators. We saw the resonance. And then we have the strong deactivators of positive formal charges, or the sulfo group, or the nitro group. Now, the one thing that is weird with our trend, we have these general rules: electron donating groups activating, orthopara, withdrawing, deactivating, direct meta. The one exception to this are halogens. So halogens are going to withdraw from the ring via induction, and then they are going to donate into the ring via resonance. But is this a good resonance structure? A positive charge? On my fluorine? No, she's not going to be okay with that. But it still happens a little bit. Like, it's not a strong resonance contributor by any means, but it is partially there. And the big thing is, we said that directing effects are controlled by resonance. So because of that, because these are donors via resonance, they are going to be up here orthopara directing like all the activators. Even though overall their effect, the thing that is stronger is induction withdrawing, deactivating the ring. And so because of that, we say that the halogens, the only exception. Chlorine, you are the only exception. Bromine, you are the only exception. Iodine, you're the only exception. And I'm on my way to getting an A. I don't know. So that is the only thing that is going to buck against these two key ideas here. Groovy. So the classic thing that you do with benzenes when you were learning these reactions. Oh, sorry. That's a lecture or a little lesson on circles. What happened? What?
Is that what you call like a 1-2 tab shift?
Oh, very funny. Very funny. Yeah, no, this is my like area circumference draft of my like SAT ACD lesson. But no, I realized I've been writing on the 1230 section the whole time instead of the 830 section. It's fine. It's fine. Okay, so a classic type of problem with benzene reactions here in directing effects is tri-substituted benzene synthesis, where we need to add 3 things onto the benzene, and we have to use directing effects to help us out. So for this one, I do not have a good reason to tell you why we are going to do it this way, other than if we are adding this bromine nitro group and then this alkyl group, it is going to be better to do this as an acylation and then a reduction. Part of it is like if we go through all the possibilities of the directing effects, it's going to be a little bit easier. This was also from when in the past we only did Friedel-Crafts alkylation for like carbocation SN1 style. Here we could do the adding the alkyl group SN2 style, and that would be fine, but our directing effects would be completely different. So instead, why don't we just imagine that this was a typo and we meant to have a carbonyl here the whole time. I think that'll make it a little bit easier. So if we need to add this acyl group, this nitro group, and this bromo group, we essentially can think through all of the possibilities and see what works. So first off, our bromo group. If we add a bromine, does bromine direct orthopara or meta? She's our one exception, orthopara. So here, we could be adding our carbonyl para to it, sure, or we could add our nitro group ortho to it as a next step. Do both of those work with our directing effects? Yeah, both of these are valid options. But now, if we had added the nitro group second and then we are adding our acyl group, what's the issue?
You can't add anything with a nitro.
Yeah, so this shuts down Friedel-Crafts. So this route doesn't work. What about if we do the acyl group second and then we need to add our nitro group? Well, our bromine is going to direct orthopara to it. And then our acyl group is going to direct orthopara or meta to it. Meta, it's a withdrawing. And oh my gosh, it's so nice. Both of the directing effects agree. So, will we be able to add our nitro group at the correct place? Yeah. And it might be like, well, how do we control this side versus this side? This is a flat molecule. We could pancake flip it. And like this with the nitro group added here is going to be the exact same thing as the nitro group added here, because it's flat and planar. So this route works. What about these other ones? So if we did our nitro group first, then could we do a Friedel-Crafts after this? No. So no Friedel-Crafts. Then if we wanted to add our nitro group, does nitro group direct ortho to it? No. So this is a meta director. So that would not work. If we started with our carbonyl first, well, in trying to add our bromine in the right position, we said that this is a meta director. So can we get bromine in this position if we add the carbonyl first? No. And then if we add our nitro group, does this add in the correct meta position? Yeah, I think so. But then let's look at the directing effects if we do our third one here. So for our nitro group, it is withdrawing. It's going to direct meta to it. So it is going to direct over here. And then our carbonyl is going to direct meta to it over here. Is that where we want to add our bromine? No. So do you see how of these, there was only one option of all of the possible combinations that could work? Now, it's not going to be helpful on a synthesis to go through all of them, but our general rules here are that we want to add our deactivating groups later. So that is one thing that you're going to see as a trend. And then another thing that you can do is you can try just doing one of them. Like if you knew that your nitro group had to be at the end, you could try either adding the bromo group first or the acyl group first. And then that can let you play through the directing effects to choose the right order. Yeah.
Wouldn't, okay, at the bottom with the acyl group and then the nitro,
Yep.
wouldn't the nitro itself just stop anything from occurring?
It just stops Friedel-Crafts. So we can still do any of our other reactions other than Friedel-Crafts. So bromination can still happen, but the bromine is just going to add at this carbon. Yeah. So again, it's kind of dense, but this is where you're going to have some conceptual questions on it. There's a lot of it in the problem set to be working through some of these. So you will see more certainly. Cool. Any questions about directing effects? Not yet. Now, one thing I want to flag, I did not have enough time to talk about aromaticity in this section, so I do have a supplemental video that's like 10 minutes where I talk through aromaticity and then I work through some aromaticity examples here. So that you can scan a QR code and watch it. I also talk about some of these other weird cases, like a side note box of what do you do when you have multiple directing groups, like who wins? And then a side note here on pi bonds that are outside of the ring. What do you do with those? So these kind of cover all like the detailed cases. But with that, I think I need to go on to how to study reactions if we want to finish kind of on time-ish. I had pulled some like substitute benzene syntheses here. Maybe we could do one. So like here we need to add a chlorine and we need to add an acyl group. So we need to figure out which one we add first. Well, what's the relationship between these two here? Meta. So which of these are meta directors? The chlorine or the acyl group? Acyl. So we need to add the acyl group first and then add the chlorine because it's a meta director. So what we would do is we would add our acyl group, and the way that we get our acyl group is just chop and then put a chlorine in its place with AlCl3. And then we would add our Cl2, AlCl3. So that's kind of the reasoning. You're not always going to have to add 3 things to a ring. It gets a little bit harder when we start off with one thing added to the ring, but then there are only 4 possibilities of like how you could do the order of everything else. So. The time has come for How to Study Reactions, Part 3. The drama, the mystery. This is going to keep going for 45 seconds if I don't stop it. So, many of you have already heard some of these ideas in our one-on-one meetings, just because that's where you were at in your studying, you were ready to hear some new ideas. But the challenge for Exam 1 and Exam 2 are very different. For Exam 1, it's like the basic skills that are all over the place, hodgepodge. You have chairs, Newman projections, what are molecular orbitals, and then also baby's first reactions. And like a lot of that, going from 0 reactions to 9 reactions, there's a challenge of like even knowing what game we're playing. Because like now you can see the game. You've seen so many reactions, you see what the challenge is, but that was not clear on week 2. And like Logan and I were trying to be like, this is the game, here it is, but like it just takes time to see it, you know? And like everyone comes in with different study strategies for it. Now that we're in Exam 2, you know the game. The challenge is a volume challenge if we have 80 plus reactions. So this is the historical breakdown of the Exam 2 questions. And one thing that you'll notice about it is 5 of the 9 questions are line reaction level synthesis. And so your line reactions are something that are going to be really, really valuable to be quick at for predicting the products and getting the reagents. There is an element of just straight up memorization with that. And it's kind of like the basics need to be down in order for you to have time to actually think through things on the exam of like the order of different reactions and like how to form these weirder products. The theory reactivity, we said 1 page of that almost completely is going to be lecture 9. And then I think in the practical exams, so I started trying to write some of the exam, but I don't really have anything. The theory, these are things like aromaticity, EAS reactivity, directing effects, CAD ranking reactivity, SM1, SM2 speed of ranking, carbocation instability, like weird short mechanism, a most basic atom. These are what were on the practice exams, just to kind of see a hodgepodge of it. With your studying right now, your first goal should be get through PSET 5 as quick as possible so that you can focus on studying for the exam and getting all the reactions in. And then the second goal is to try to have all of the basics of the reactions, of being able to produce the mechanisms, the line reactions, and the reagents by like Sunday or Monday. Just because like you are going to need directed time to practice in order to build the skills of, okay, I have the basics down. How do I assemble these molecules, think through synthesis, all the mechanisms and everything? And so, again, the most effective strategy I've seen is the little 3-minute exercises, the die drills, anything that does active recall, go with that. And you can see how to study reactions from last Friday, how to study reactions part 2. I want to introduce like the other part of studying. Like after you have the basics down, what do you do? And essentially there are 2 kind of challenges that your studying has to address in some way. One is the issue of tractability. Right now, if you just had a list of 80 reactions, it feels very spread out, it feels very intractable, and we need a way to organize that, to give it a kind of conceptual framework and to group things together that are similar, so that you're not memorizing a list of 85 reactions. You're memorizing a kind of shorter list of groups. And so my way of doing this is using reaction families and using kind of like a study sheet. So you've seen my reaction summary sheets from like lectures 3 and lecture 5. I have a web today for lecture 9 things. I think thinking about it as families, I also did this out. I was like, okay, there are about 14 families in total. And that to me feels a lot more manageable than we have 85 plus reactions. And so it's just kind of grouping things together so you know where everyone is at. Then the second issue to address in your studying somehow is integration. So right now y'all are really good at thinking of, okay, I'm in lecture 8 mode, I'm going to do my lecture 8 reactions. Lecture 3 mode, do lecture 3 reactions. But we need to be able to ping pong, to bounce around between all the different reactions. And like I'm intentionally trying to write synthesis questions that use a reaction from every lecture or something. Like it is a goal for us to see, can you put it all together? So there are 3 strategies I want to introduce that kind of work on that integration issue. So the first one I call the nature walk. So start with some small molecule and then just try to turn it into other things. So an alcohol, let me make it a leaving group. TSCl, pyridine, OTS. Okay, well now it's a leaving group. I can do substitution elimination. Let me add a nucleophile. Let me add like NaCN. Okay, now we have nitrile. What can I do with nitriles? Well, lecture 5, I can nitrile hydrolysis. That's H3O plus this. Now I have a new carbon up here from the CN, and that's going to be an OH. Okay, carboxylic acid. I'm in CAD land. Ooh, or I could leave CAD land. I could do reductions. Like, I could leave CAD land and suddenly I do lithium hydride.
And get a second
2O. Yes, H plus workup. This could give this alcohol. And now I'm back in alcohol land. I can do all the alcohol things. Or from here, I could do like NH3 DCC. I could make an amide. Then if I want to, I could reduce the amide. But just like see where it takes you. Like be like, can I just keep walking through reactions? See what gives me dead ends. See what things you don't know reactions for. See, okay, if I go back and did a different path, what would happen? It's a good just kind of like mind map strategy that doesn't have a lot of pressure involved. And also it can be like, oh, I want to turn this into a carboxylic acid. Do I remember the reagents for that? And so you can do a little practice with that. Strategy 2, friend syntheses. So do y'all have friends? Kinda? Yeah, particularly in the course. Do you have some friends in the course? I should have started with that. I think one of the best ways to study for synthesis, because synthesis, you can't just like look up more problems online, because every OChem class has a different set of reactions for synthesis, and there are no other classes that use exactly our set. So the only other people who know what you are going to be tested on are the people in this class. So find a buddy or 2, be like, hi, we are gathered here today to exchange synthesis questions. Throw a potluck. Say, okay, by Monday evening, each of us are going to write 2 synthesis questions that are 8 steps. And what you do is you make sure you have a blank version with just the starting material and the products, and you have an answer key that you have written, and do a big swap. And then if you are that girl try to stump your friends. Be mean, be rude, but also be correct. Because if you try to draw a like really hard synthesis and then they're like, girl, that doesn't work. Very embarrassing for you. Very embarrassing. But I think it's a really great exercise to write synthesis questions because I think it frees up synthesis to be like a little bit more of a fun space. Whereas right now it can seem like a very deathly scary place. It also gets you in the mindset of us writing your exam of like, I spent an hour in lecture just like brainstorming different things I could do with like reactions of syntheses. What would be cool? What would be interesting? Which maybe are crazy questions to ask for an exam. What would be a cool question? But I think it gives you permission to think kind of creatively about this rather than necessity. I have to do it this way. And yeah, I think that will be helpful. So throw your synthesis potluck. Like, go ahead, like, message people, set a date, because otherwise they'll get too late and you'll be like, not worth it. Thoughts on synthesis potluck. Friend syntheses. Last one is reaction webs. So these are one of my favorite ways to work on integration. What you do is you pick a functional group on a specific small molecule, and then you think of all the reactions that you can do that start with that molecule, or all the reactions that produce that molecule. What are ways that we can make a primary alcohol?
The
Carboxylic acid, great. And we do lithium aluminum hydride. What else? Come on, y'all.
Something with CrO3PYR.
So that's going to take carboxylic acids to do something else. So we can do that. So if we do CrO3 with pyridine, what does that turn this into? With pyridine, aldehyde. And I also think it's good to label your functional groups here just because it gets you thinking in functional group mode. And those are, remember, are tags between all these reactions. Okay, what if we did CrO3 and H2O? That gets us to our carboxylic acid. Great. So we have our redox ones, like lecture 5. Throw more. Anything with an alcohol. Turn into a leaving group. So what are ways that we can do that? TSCL. So OTS. Then what about turning into a bromine?
Alright, SN2.
Yeah, but what's the reagent? PBr3, yes. Cool. And now it's an alkyl halide.
There was also SOCl2, right?
Exactly, and that turns it into a chlorine. So this is also alkyl halide. What else? Other ways of making alcohols. What else could we reduce? And look at our chromium. Instead of reducing carboxylic acid, we could reduce an aldehyde. For a ketone, we could, but it wouldn't be a primary alcohol. Yeah. Okay. Any other ways of making alcohols? What about from an alkene? What reagents could we use to make from an alkene? H3O plus is great. You could also do hydration, oxidation, or mercury. Those feel like overkill for this small molecule, but there are those. And then other ones that are even weirder. What if you added a carbonyl and H+? That's our good friend, the acetal reaction, all the way from lecture 3. And then what if we add a carboxylic acid and H+? Well, next gonna make an ester from lecture 5. And then I have one other thing listed. What is it? What if I add NaH and like MEBr? What functional group does that turn into? Yeah, that's our Williamson ether synthesis. Already, just from this, we're hitting lecture 5, we're hitting lecture 7, we're hitting lecture 3, 5 again, 7, 8. And then once you find all the ones that you can template this, so erase what you have, and then be like, okay, can I think of all the things that we can make from it and all the things that we can turn it into? It's a really, really great study tool. I want to do one more really quick. So primary amines. What are the 2 ways that we can make primary amines? And hint, this was in lecture 5.
Reduce of nitrogen.
Yeah, so we can reduce an amide, or we could reduce a nitrile. And both of these, I'm just going to write LAH, lithium hydride ET2O, step 2, H plus workup.
Can you hydrolyze an imine to make?
So you can, but we didn't teach you that. But yes.
Wait, you did. It's in the.
Oh, actually, I see what you mean. So you're saying, could we do like this
Yeah,
with
yeah.
H3O plus, and that's going to spit off great work. And then things that we can do with a primary amine, well, we can really turn into an amide, or we could like do an imine here. So we could do all the way back to this imine if we did this carbonyl, pH around 5, or we could do with like DCC and a carboxylic acid. Here we can make an amide. So we have amine, amide. So again, this also kind of gamifies it a little bit, which I think makes it a little bit less dull, because the dyes can be a little bit dull. But this primarily for synthesis and line reactions, stellar strategy. It gets you to work on the speed of brainstorming the different reactions that are connected to things, which is going to be useful when we are kind of putting it all together. And so with our last 10 minutes, let's look at a hard synthesis. Are y'all ready? Are you filled with determination? Are we gonna get through it?
Yeah.
Sounds like a poor Victoria child. Yeah. Okay. 11 steps. We go from the top little boxy boy to her. So, when we are faced with things that seem impossible, what we need to do after like giving ourselves 30 seconds to panic is go back on our laurels. We know that we can analyze functional groups. Another thing that I would suggest doing is number carbons. Do we have the same number of carbons in our starting materials and products? Because that can tell us if we've done any other reactions. And then third things, think about functional groups where we don't know a ton of reactions. So alkenes, we know a ton. Primary amines, which we just did a brainstorm on, we only know a few ways of making. So I'm going to give you like 2 minutes to try to do some analysis. And in that time, what I want you to do is try to do some brainstorming, functional group analysis, mapping starting materials from the products, number your carbons, and then think about goals for what are some like big things this reaction has to do. That is all I want at this point. So 2 minutes trying to think through it. And does everyone have something written down to look at this if I like navigate away? Yeah, totally. So this is the analysis that I've done in a couple of minutes, just to kind of show where it's at. So I saw we had alkenes in the start and primary amines in the products. I counted carbons. I saw that there were only 6 carbons in the starting materials. There were 8 carbons in the product. And then brainstorming-wise, primary amines, we only know a few ways to make, and so I kind of drew out the options for what we could have done. We could have either had nitriles or amides and then reduced them. We could have had amines, but that seems like it's going to be more work at this point, right? There are certain circumstances where the amine would be a smart strategy. So the big thing that I'm thinking of, like the issues of this reaction, we have to bust open a ring. Now, when you think about breaking open a ring, there should be overwhelmingly one strategy that comes to mind for synthesis. Does anyone happen to know what it is?
Radicals.
So radicals, it does bust open a ring. We saw that earlier, yes. But she's messy, right? She can do a lot of weird things. So we typically don't want to rely on radicals in a synthesis. We only want to do the most straightforward radicals in a synthesis. So that's a great thought, though. Like radicals, messy. What is our reliable way of busting open a ring? Ozonolysis. So, yeah. Side note. I used to call this reaction something that's a little bit inappropriate. Can I tell a slightly inappropriate, like, joke or thing? I've learned now. I didn't know that was inappropriate before, and that's what is a little funny. So I used to call this reaction Lord Split Me Open, because it's like, just split it open. Because I thought that phrase was a sincere religious experience and then was co-opted by memes online, and it turns out it is not a sincere religious experience. I thought it was like, Lord, break me open, but no, that is not. But short story, now you'll never forget ozonolysis, Lord Split Me Open. Like, it is the go-to way of busting open a ring. Yes, so there is that. And then when I realized that that is not the case of it being a common religious, like, experience term, I was very embarrassed, deeply embarrassed. So, ozonolysis. So in order to do ozonolysis to bust open a ring, what we need to do is we need to get an alkene on the ring. So right now our alkene's over here. Somehow we would need to get over here. That's kind of thinking on those terms. And then the other big issue is we have to add 2 carbons somehow. What are ways that you have learned of making carbon-carbon bonds? Grignard, what else? Yeah, that's kind of the same family. Wittig from lecture 8. We know that's a really powerful way of making carbon-carbon bonds. The other one, SN2 with a CN minus. If we think about these 3 strategies, and we also think about, hey, our primary amines had to have come from a nitrile or amide, what do you think is a strategy that we should go for? I think the SN2s. Like, we have 2 kind of pieces of evidence that would suggest maybe that this is going to work. And it might not, but I think it's worth trying. So, do you think that we have some directions so far? Okay. So, in order to do this SN2 route, what we need is 2 leaving groups over here. So, that is kind of where we are first going to head, getting leaving groups and getting our alkene on a ring. And if it's okay with y'all, I'm going to take 5 more minutes to try to finish this out. And again, if you have to go, you have to go. Totally get it. So, over here, in order to get an alkene on a ring, like let's say we wanted to get the alkene over here or something, we need to get a leaving group that's closer to the ring, right? Like we want something like maybe a bromine here. We could imagine kind of scooching it over. Or if ideally we had like a bromine over here or something, then we could easily do an elimination on this. But that's going to be kind of hard to get a bromine all the way over here. Why don't we just try adding a bromine to this alkene? So if we did HBr, what's our product going to look like? That's what we would think. So this is what we would think. But in fact, remember, whenever we do acid additions, we have to think through the carbocation that's formed. And what can this carbocation do?
Hydrogen?
A ring expansion. That's fun and fresh and fancy. So here, what we have, carbocation. And then, in fact, we're going to do one more little shift. And so our best product from this puts our carbocation on this tertiary one in the ring. Now, if you did not clock all of these rearrangements here because this is such a strained thing, that is fine. There are ways that we could get to the product and it would be like a half point deduction just if we didn't get all the way to the more like stable carbocation. But at the end of the day, we are going to get a 5-membered ring now with a bromine on a ring. Does this look like something that we can do an elimination with? Yeah, we have a good leaving group, right? So if we want to do an E2 elimination, what should we use? Some sort of base. Yeah, throw out a base. I'm going to do OME. Yeah, home. Naomi. So then with this, what we get is an alkene in the ring. And now are we ready to bust it open? We are indeed. So let's use ozonolysis. Okay, ozonolysis has 2 flavors. We have the second step as DMS, or we have it as H2O2. I don't think it's going to matter super much which way we do, so let's just try one. Let's try DMS. So when we do that, we cut along here. And remember, we put carbonyls where our double bond was. And then one thing I'm also going to do is there's a little hydro on this side, so I'm going to write it this way so it looks like an aldehyde, which is a little bit easier. So with this, we've accomplished our first goal, busting the ring open in the ozonolysis. So now we need to figure out how to do the second part, which is get those nitriles on there, right? So we have this structure of a nitrile, and we could think back one step further, and we could be like, well, we just need something that's a good leaving group for SN2. What if we had like a bromine? So if we look at this, this is going to be 1, 2, 3, 4, 5, 6 carbons. We have a 6-carbon chain, 1, 2, 3, 4, 5, 6. So I'm kind of mapping these carbons, or these carbons here. I need to turn an aldehyde into a bromine. We don't know any reactions that do that directly, though, right? How have we made bromines in the past? Yeah, we could do it from an alkene, with like an HBr or HBrOR. What other ways have we made bromines? Yeah, we can make it from alcohols. So which do you think will be easier to get to from an aldehyde, an alcohol or an alkene? Alcohol. We could do it from both. It's just alkene's going to require more steps. So let's do this. So we need to get this down to an alcohol. So we can reduce NaBH4, MEOH. We have OH here, and now we have an OH, or one more carbon, sorry. And I'm just going to redraw this to make this seem a little bit nicer. I'm going to draw it kind of like I have the product. So 1, 2, 3, 4, 5, 6 carbons. Now we turn it into our bromine version with our PBr3. Now, are we ready to do our nitrile? I sense fear from everyone. You're like, oh, this is going to be our exam? This is a very hard synthesis. This is one of the hardest ones we've seen so far. Kind of like last Friday, we saw a really hard synthesis. And so I think it's worthwhile to do them together. So now we have accomplished our second goal of we've added 2 carbons, and the carbons came from the carbon in the nitrile. So now our last thing, the only thing that we have left to do, is 1 lithium aluminum hydride, 2 H plus work up. And that's it. So this was a lot, and there are often times, or like I bet there were steps in this process that is like, oh, I never would have thought of that. I think getting to where you can reliably do your analysis, that's going to set you up for how to be thinking about this, that is part 1. Part 2 is getting the reaction basics down. So if you think about, okay, I need to bust open a ring, ozonolysis comes to mind. I need to make carbon-carbon bonds. Okay, I have Wittig, I have the organometallics, I have SN2 with cyanide. Oh, I need to make an amine. We can only do it from an amide or a nitrile. Those are the things that you're studying is going to do to help make this achievable. And in the end, we had 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. So these are getting big. You guys have got this, though. I hope this was helpful in kind of seeing some of this together. Thank you for letting me go over. Gosh, it was 10 minutes. But I hope you have a great rest of your day and a good weekend. And I will see y'all on Monday. Goodbye. Yes.